In the following video demonstration, we will build a simple data lake on AWS. Using a combination of AWS services, we will move data from 3 separate data sources into our Amazon S3 based data lake. Once in the data lake, we will perform ETL, or more accurately ELT, on the raw data, preparing it for data analytics and machine learning. Agenda. First, we will define what a data lake is. Then, I will describe the data set we will be using in the demonstration. Next, I will let you know where you can find all the open source code for this demonstration on GitHub. Next, I'll review the architecture used in the demonstration. And finally, we'll spend the majority of our time in the actual demonstration. What is a data lake? First, from Databricks. A data lake is a central location that holds a large amount of data in its native raw format. Compared to a hierarchical data warehouse, which stores data in files and folders, a data lake uses a flat architecture and object storage to store the data. Next, the definition from AWS. A centralized repository that allows you to store all of your structured and unstructured data at any scale. You can store your data as is without having to first structure the data and run different types of analytics, from dashboards and visualizations to big data processing, real-time analytics, and machine learning to better guide your decisions. A data lake is only part of a typical analytics platform. Normally, we start with data ingestion, using different tools to securely move data from multiple data sources into a data lake. We then inspect the incoming data for such things as anomalies, malicious content, and unexpectedly sensitive data. The raw data is then transformed into a format and structure optimized for analytics and machine learning. Finally, the data is ready for data scientists and data analysts to perform analytics and machine learning on. The data set for this demonstration is the ticket database. The ticket database is provided free by AWS. It represents an e-commerce platform which brings together buyers and sellers of tickets to entertainment events. It was designed for demonstrating Amazon Redshift, but we will use it to build our data lake. The ticket database is a small database consisting of 7 tables. Those tables are the categories, events, venues, users, listings, and sales for our events, and the dates that the tickets were purchased. This is a diagram which represents the tables and their relationships to one another. Data lakes usually represent data from multiple data sources, each with different formats, protocols, and connection methods. To simulate this, I will split the ticket database, the 7 tables, into 3 separate data sources. The category, events, and venues will represent tables coming from a software as a service or a third-party vendor. I have moved those into Amazon RDS for PostgreSQL. Next, the listing, sales, and dates of the transactions represent data coming from an e-commerce platform. I have moved those tables into an Amazon RDS for MySQL database. Lastly, to simulate a third data source, the users will come from a customer relationship management or CRM system. I have moved that table of users to a Microsoft SQL server. So we have an Amazon RDS for PostgreSQL, an Amazon RDS for MySQL, and an Amazon RDS Microsoft SQL server. So we have 3 different data sources, which will represent 3 different data sources, including a SaaS provider, an e-commerce platform, and a CRM system. The source code for this demonstration can be found at github.com/Gary Stafford/ticket-data-lake-demo. First, the services we'll be using in our demonstration. I will be using AWS Glue Studio, AWS Glue Data Catalog, AWS Glue Crawlers, AWS Glue Jobs, AWS Glue Data Brew, Amazon Athena, and Amazon S3, in addition to the 3 database engines on Amazon RDS. On the screen you see a diagram which represents the architecture for our demonstration. On the far left you see our 3 data sources, the PostgreSQL, MySQL, and SQL Server data sources. In the center of the screen you see AWS Glue. We have a series of crawlers that will crawl our data sources and catalog the schema and metadata information into an AWS Glue data catalog. We then have a series of AWS Glue Spark jobs, which will extract the data from our data sources and place it in a raw or bronze area of our data lake in Apache Avro format. We have a second set of AWS Glue Spark jobs, which will transform the raw or bronze data in Apache Avro format into a more refined or silver format data in a different part of our data lake in Apache Parquet format. Lastly, we have Amazon Athena. We use Amazon Athena to further transform the silver refined data in Apache Parquet format into gold or aggregated data and partition that as Apache Parquet. The gold or aggregated data will represent the final format of our data, which we'll delivering to our stakeholders or further downstream for analytics and machine learning. Since this is a simple demonstration, we can't possibly incorporate all the processes that normally go into building and managing a typical production-ready data lake. However, since these are critically important items, I want to at least quickly review what is out of scope before continuing. CDC, or change data capture, how to handle changes to the system of record or data sources. Transactional storage layer, incorporating technologies such as Apache Hudi, Apache Iceberg, or Delta Lake to actively manage the data in our data lake. Streaming data, using technologies such as Spark Structured Streaming, Kinesis, or Flink. Fine-grained authorization, database, table, column, and row level access to the data in our data lake. Data lineage, tracking data as it flows from its source to consumption. Data inspection, scanning incoming data for sensitive information such as PII. DevOps, or data ops, automating testing, deployment, and job execution as it relates to our data lake. Data warehouse, or data lakehouse architecture. Data lake storage tiering. These are the items that will be out of scope for our simple data lake demonstration. Demonstration. We will now spend the majority of our time walking through the demonstration. I'll use a combination of the AWS CLI from the command line and the AWS Management Console to build our data lake based on the architecture shown previously. Before beginning the demonstration, I will walk through some of the resources I've already created within my AWS account. First, I have an Amazon S3 bucket, which represents the data lake. Within that bucket, I've created a ticket directory, or key. As we proceed through the demo, the raw, refined, and aggregated data, or the bronze, silver, and gold data, will be written to this location. Next, I've created a glue data catalog to hold the metadata and schema information about the data in our 3 data sources and eventually within our data lake. Currently, the database contains no tables. Next, I've created 3 AWS Glue connections. These 3 connections contain the connection information required to securely connect from AWS Glue to the 3 data sources, the PostgreSQL, MySQL, and Microsoft SQL databases that contain our ticket data. I also have 3 AWS Glue crawlers. Using the 3 AWS Glue connections, the crawlers will extract schema and metadata information from the tables within the 3 data sources. The crawlers will then create a series of 7 tables representing the 7 tables within our data sources in the AWS Glue data catalog. Those tables will contain the schema and metadata information about the tables of data in our 3 data sources. Lastly, I have a series of 14 AWS Glue Studio jobs. The first set of 7 jobs will extract data from our 3 data sources using the information in the AWS Glue data catalog. The jobs will write the data into the raw or bronze area of our data lake as Apache Avro file format. The second set of jobs, _refine, will perform basic ETL on the raw or bronze Avro data, cleaning it up for future analysis and writing it into the refined or silver area of our data lake as compressed Apache Parquet file format. As part of the AWS Glue Studio jobs, a new table representing either the bronze or silver data in the data lake will also be written to the AWS Glue data catalog. I've created all the commands that I'm going to run from the command line ahead of time. You can see here I'm in PyCharm. I have all 3 of my databases, so again we can see the distribution of tables across the different databases. In my Amazon RDS MySQL Server database, we can see the users table. In the Amazon RDS MySQL database, we can see the date, listing, and sales tables, fully populated with all the data. And finally, in the Amazon RDS PostgreSQL database, we can see the catalog, event, and venue data. So this is the information that we're going to first use our crawlers to extract the metadata and schema information from, and then eventually we'll use that information to extract the data from the databases, write it into the raw area of our database, and then continue to refine it. So as I mentioned, I've already created the S3 bucket. I've already created the Glue data catalog. It's empty. So the first thing I want to do is start the 3 crawlers. The 3 crawlers will run and it will extract the schema and metadata information from the 7 tables and place that into our AWS Glue data catalog. As these crawlers finish, I would expect to see 7 tables in the AWS Glue data catalog. I'm going to go ahead and start those running. I'm going to start all 3 of those running at the same time. Once they start, I'll flip over to the console, I'll show you that they're running, and then I'll pause the video until they complete, and then we'll look at the results. So we can see that the 3 crawlers have now started. So we can see that the 3 Glue crawlers are in the process of stopping. We can see on the far right-hand side of the screen under Tables Added that we in fact added a total of 7 tables, 1 for MS SQL, 3 for MySQL, and 3 for PostgreSQL. As those are stopping, I'll flip back to the AWS Glue Data Catalog and hopefully we'll see some tables. So I'm back in the ticket underscore demo AWS Glue Data Catalog. And in fact, we do see a total of 7 tables. Note under classification, we see SQL Server, MySQL, and PostgreSQL Server. So these are the sources of data. These are the database engines that we used our AWS Glue connections. You remember we talked about our connections. So we had our 3 JDBC connections, which allowed AWS Glue to connect to our catalog securely using a JDBC connection. Using those connections, the crawlers then crawled that data, extracted metadata and schema information, and wrote that into the tables. We see the database, we see the location, we see the database, the schema, and the table name, and we see the different database engines from where they were extracted from. If we take a look at these tables, again, if you're not familiar with AWS Glue, it's a Hive-compatible metastore, which means it's not storing the actual data. We haven't extracted any data from the databases yet. We haven't moved any data into our data lake yet. We've simply cataloged the metadata and schema information about the tables in our 3 data sources. So we can see here some basic metadata information, and we can see our schema, the column names and the data types. There's no partitions, there's no comments. So very basic information about that. The other thing we know is we have the connection, so we know where the data is. Next thing we'll do is run our first set of AWS Glue jobs. The AWS Glue jobs will use these tables, the information in these tables, and we'll use the AWS Glue connections to extract that data. So now we'll actually move the data from the data sources into the raw part of our data lake in the next step. So I'll flip back over to our AWS Glue Studio jobs. Again, you recall I said we had a series of 14 jobs. 7 of those jobs, which represent the 7 tables across our 3 data sources, or the underscore convert, we're going to convert or ingest that data from the data source into the raw area of our data lake. So we're going to run the 7 convert jobs. Once that's done, that data will then reside in our data lake, in our raw area of our data lake, and we should have another series of tables in our AWS Glue Data Catalog, which contain the schema information and metadata information about that Apache Avro format raw data in our data lake. Again, I have all the commands written, which is much quicker than going through and clicking on 7 different jobs in the console and running those. So let me flip back to my command line. I'm going to start those 7 jobs, then we'll take a look at them running. So again, 7 jobs, 1 for each table of information across our 3 data sources that we want to extract. So let me start those running, and then I'll show you the jobs running and what the jobs look like. So we can see that those jobs are being queued up. If we flip back over to our AWS Glue console, we can go under monitoring. Let's just make sure they're running before we look at the jobs. We can in fact see that we have 7 jobs running. So those 7 jobs are running right now. They're using the AWS Glue Data Catalog tables, the schema metadata information, and the AWS Glue connections to start extracting the data from those tables in our data sources and writing it into our data lake in Avro format. If we look at these jobs, let's go back and take a look at one of the jobs. They're all very similar. Again, we're running the convert job. So I'll look at the ticket public listings convert. So this is the listings table. All the jobs are similar. For an AWS Glue Studio job, the most basic job is a source, transform, and target. This is even simpler. We simply have a source and a target. So we're not doing any transformation yet. We just want to move information from our source to our sink, or from our source to our target. So you can see here the ticket underscore AWS Glue Data Catalog, the raw underscore ticket underscore listings table. We're going to extract that information, the underlying information, from the database engine. And we're going to write that back to a different location in our data catalog and also in our data lake. So the information will be written to our data catalog, the schema information, and the physical data will be written into S3 bucket, into the bronze or raw area of our data lake, and into this location. So you can see I have the location here. It's within our bucket, within the ticket directory that I showed you earlier, within the bronze subdirectory, and then within the listings directory. So what I would expect to see when this job finishes, actually when all 7 jobs finish, what I would expect to see in our S3 bucket within the ticket directory is a bronze subdirectory. Within that subdirectory, 7 subdirectories. Within each one of those subdirectories, 1 or more Apache Avro files, which represents the data that was extracted from our 3 data sources. So we'll go ahead and let those jobs finish. They should only take a few minutes. So now if we go over to our data lake, let's start in our data lake. You remember we had the ticket directory and it was empty when we started, so let me refresh that. So that's a good sign. We see the bronze directory. If I look in there, we see 7 subdirectories. Looks good so far. That means that the AWS Glue jobs were able to create the directory structure within our data lake. If we go into categories, for example, we do see a series of Apache Avro files. Using tools like AWS Glue, using Amazon Athena, using Spark, using additional tools like Apache Hudi or Iceberg, you're not actually managing the files in Amazon S3. Amazon S3 is just a data store. How these tools store the data, how many directories, how many files, really shouldn't be of concern to you. Now, if we get a lot of very small files, that can slow down our analytics engines. We have ways to optimize that, read those files in and write larger files. But you're not physically going into Amazon S3. You're not opening files. You're not physically managing those files in Amazon S3. The tools that we're employing to build and manage our data lake are managing those files. So don't worry about the file structure, how many files there are, how many directories there are. We're not going to worry about that too much. If I go into a different folder, let's go into sales. We see a similar series of files. Our jobs worked. We now have data which was extracted from our 3 data sources. That data was cataloged in AWS Glue Data Catalog. I'll go over there and show you the tables in a moment. And the data was written into the bronze area of our data lake. So if I go to tables now, we actually see 14 tables. So we had our 7 original raw underscore tables. So that's the schema and metadata information about the data in our data sources. I now have 7 additional tables prefixed with converted underscore, which represents the raw or bronze data in our data lake. So what's next? We have this raw data in our data lake. I'll go back to our diagram for a minute in our presentation just to remind us. We've ran our crawler, step 1. We've extracted the schema metadata information to our AWS Glue catalog. We just ran step 2. So we ran a series of 7 AWS Glue jobs. Those use Apache Spark. Those jobs extracted the data from our database engines using the AWS Glue data catalog and wrote those into our data lake, into an Amazon S3 bucket, into the bronze or raw area of our data lake in Apache Avro format. So our next step, or step 3, is going to be to run a series of jobs which will take that raw or bronze data. It will perform some cleanup on it. It will clean up dates. It might get rid of null strings. It may delete some columns that we don't need for further analysis. Maybe it's sensitive or PI information that we don't want our data analysts to be able to see. So we'll clean up those files. We'll perform some basic ETL. The actual ETL performing really isn't important. It's more the process that we're demonstrating here. So we'll take that raw data, we'll refine it, we'll clean it up, we'll cleanse it, and we're going to write that from Apache Avro. We're going to write that into Apache Parquet. So we'll read in the Apache Avro. We're going to write out Apache Parquet. Apache Parquet, if you're not familiar, is a columnar format. It's more optimized for analytics purposes, and it's also written in a compressed format. So we'll have compressed Apache Parquet files that we could directly perform analytics on, or we can perform some additional aggregation on. Maybe we want to combine some tables together. Maybe that final data set that we want to expose to our data analysts and data scientists, we want that to be a little more refined, maybe a combined aggregate of a couple different tables. So we'll do that with Amazon Athena. But first, let's complete step 3, which is to run the second set of AWS Glue jobs. So again, I've already written the commands to run those jobs. Let me clear this out. I'll run those jobs from the console. I'll start those jobs from the console, and then we'll flip back and look at those running and see the end results once they finish. So again, 7 jobs representing the 7 original tables of information, representing the 7 directories of Apache Avro files that are now in our data lake. So those jobs look like they successfully started. If we go back to our AWS Glue Studio tab, and again, you remember those jobs were 14 jobs, 7 for raw, 7 for refined. So we're running the 7 jobs now for refining the data, performing ETL on the data. We see that all 7 jobs are running. Go ahead and take a look at one of the jobs just to get a sense for what we're doing with those jobs. So let's look at the ticket underscore public underscore listing underscore refine job. So this is a typical job. This is a very simple ETL. So we're reading in the ticket underscore demo, AWS Glue data catalog. Table is converted underscore ticket underscore public underscore listing. So that's our raw data that we brought in. We converted it from our databases, ingested it, converted into Apache Avro, and wrote that into the bronze or raw area of our data lake. We're reading that table in. In this case, we're performing a very simple ETL. We're just dropping the total price. We know the number of units and we know the individual price. So total price is really an extraneous field. We don't need that. We're going to go ahead and perform our own computations on those columns. If we need to get the total price, we'll go ahead and do that as part of our aggregated query. And then we're taking that information, so again, reading in the Apache Avro format data, and we're going to write that back into our data lake, and we're going to write that into a new location, into the silver location of our data lake, and again, under the listing subdirectory. And we're writing that as Apache Parquet using snappy compression. So as these jobs finish, I would expect to see some additional directories in our data lake. So we can see that 6 out of 7 of those jobs finished. As that's finishing, we'll go over to our data lake. Let me just take one more look here and see if that job finished. Okay, we have one running. So we're back in our data lake, and we do in fact see two directories now, both bronze and silver. So that second set of jobs looks like it worked. It was able to create the silver directory or key path, representing each of the 7 tables which we imported into the raw area of our database. If I open one of these, I would expect to see a series of Apache Parquet format files versus Apache Avro. So we'll go ahead and open listings. And in fact, we do see, in this case, 20 Apache Parquet format files using snappy compression. We can actually view these files. So let me click on one of these files. We can view the contents of individual files for particular formats using something known as query with S3 select. So using query for S3 select, we know we have Apache Parquet format. I'll put that as JSON, and we can do simple select statements against the objects that are in that file or in that Parquet file. So let me run this query, and what I would expect to see is a series of, and we see those here. So again, we were looking at the refined listings. So this is the listings data. And in fact, we see a series of 5 listings. So we see the listing ID, the seller ID, the event ID, the date ID, the number of tickets purchased, the price per ticket, and the time at which it was purchased. And you remember we dropped the total price because we know the number of tickets and the price per ticket. So that field was extraneous. So it looks like our job worked. Just checking this first one, it looks like it worked. Let me go and look at a couple other directories just to make sure that everything is working. I'll go into venues. And in fact, if I go into venues and look, it looks like we do have Apache Parquet format files. We have 20 objects. So it looks like all of our jobs work. Next, we'll continue on and we'll use Amazon Athena to perform some aggregation of the silver data, the refined data. We'll aggregate that data. We'll create some custom views for our data analysts, and we'll write that into the gold or aggregated area of our data lake. Let me switch back to the architectural diagram for a moment. Now that we've completed steps 1, 2, and 3, we'll move on to step 4, the final step in the demonstration. In this step, we'll use the metadata contained in our AWS Glue Data Catalog and the data in the refined or silver area of our data lake to create a few final aggregated data sets, which our data analysts and data scientists can use. We'll write those data sets to the aggregated or gold area of our data lake. Instead of using Glue jobs to transform and write the data back to our data lake, we'll use Amazon Athena. Amazon Athena is AWS's ad hoc query engine based on Presto. Using ANSI SQL style statements, we can query data in our data lake, create views from that data, and also write that data back to our data lake in multiple file formats. A view in Amazon Athena is a logical, not a physical table. The query that defines a view runs each time the view is referenced in the query. So we can have a complex query statement, save that as a view, and then write a simple select statement to call that view and display the results of the view and the underlying SQL statement. In order to write files back to the gold or aggregated area of our data lake, we'll use a CTAS or create table as query in Amazon Athena. A create table as select or CTAS query creates a new table in Athena from the results of a select statement or other queries. Athena stores the data files from the CTAS statement in a specific location in Amazon S3. In this case, we'll be writing partition Parquet back to the gold or aggregated area of our data lake using CTAS statements in Amazon Athena. So I've already written a few statements. I have the Athena console open. You'll notice before we write any queries, on the left-hand side, I have 14 tables. So in my ticket underscore demo AWS Glue Data Catalog, we have 14 tables. We have our 7 tables converted underscore prefixed, which is a raw Apache Avro format file. This is the data that we extracted from our 3 data sources. We then have 7 additional files, the refined underscore files or tables. These represent the Apache Parquet files. This is the data that is in the refined or silver area of our data lake. These tables, the refined underscore tables, the data that's in the silver area of our data lake is what we're going to be querying, and also what we're going to be using as the basis of our CTAS statements. We're going to be performing additional ETL on that. We're going to be aggregating those tables together, and we're going to be writing those aggregates back to the gold or aggregate area of our data lake. I'll start with a simple query. So all we're going to do is we're going to look at the sum of all the sales, and we're going to look at the sum of the commissions, and we're going to view that by month and year. So a very simple query. We're joining the refined ticket public sales table with the refined ticket public date table. So this is the refined data in the silver area data lake, and we're just doing a simple join just to see if we're able to query that Apache Parquet format data. And we see that we were able to do that. We get 12 results back for the sales during the 2020 year and for each month of the year. So 12 results back, took about 1.2 seconds. Have a couple choices. So if this is a query that I wanted to save, I could save that so I don't have to rewrite that query in the console. So we could save that. So anytime I need to rerun that query, I can simply go to Save Queries and then rerun that query. The other thing we can do is we talked about views. Although this is a very simple query, if we wanted to save this view and able to perform simple select statements on that view later on without rewriting this more complex query, we could save this as a view. So we'll go ahead and run that again. And then we can simply say create, and we can say create view. So we might do something like view ticket sum sales. Now, if we save that, when we save that, that's actually written a view back to our AWS Glue data catalog to the ticket_demo catalog. So now, in addition to 14 tables of metadata and schema information, we have a view, and we can see the view here. We can form a simple preview on that, which will do a select star limit 10. So we have a select star limit 10 from that view. That's ran, and we can see we get back similar results. Run that one more time so you can see it. So we were able to call that view and do a simple select statement from that view and get that data back. So that's how you save a view. Let's move on to something a little more complex. We're going to do two CTAS or create table as statements now. Let me grab the first one and then I'll explain what we're going to do with it. So we can see that we have a create table as statement, aggregate _ ticket _ sales _ by _ category. So sales by category. We're going to be writing Apache Parquet data back to the gold or aggregated area of our data lake. We're going to be using snappy compression. We have the location in our data lake. You can see the ticket key or ticket subdirectory, and then we have a new area for the gold data or the aggregated data. And again, we're saving ticket sales by category. We're going to be partitioning that by category group and category name. Once I write this table, we'll go in and take a look and see how that data has been partitioned as Parquet. Simple select statement. So we're doing a join across 6 of the tables. We're doing some basic SQL functions across that. Nothing too complex. We'll go ahead and execute that. So again, this is using the SQL statement to query data and then writing the results back into S3. So we see now, if we look on the left-hand side of the screen, we have a new table. So we have 15 tables in our AWS Glue data catalog. We now have aggregate _ ticket _ sales _ by _ category. And we see that it's partitioned. The best way to see those partitions is I'll flip over to S3 and we can take a look at that. So we've ran this first CTAS query or create table as query. So if we go into our S3 based data lake, we can see in addition to the bronze and silver areas of our data lake, we now have a gold area. So this represents the final or aggregated data sets that we're going to share with our data scientists and data analysts. If we go into the gold area, we can see that we have the ticket sales by category, and within that we see our first set of partitions. So our parent partition is the category group, and we have concerts and shows. If I go into one of those category groups, we have category names. So now I have musicals, operas, and plays. If I drill into one of those a little farther, I should see a single partition file. I did use a bucket of one, which forced the individual Parquet files back into a single Parquet file. By using a bucket of one, we've coalesced those back into a single file. This single file should contain all of the shows in the show category, in the music subcategory or category name of musicals is in this Parquet file. We can take a look at this Parquet file. You can remember we have the query as S3 select, so I'll use that to take a look at this data. Again, it's Apache Parquet, and we'll view that as JSON, and we'll just do a simple select star from 5 objects. We'll execute that, and I would expect to see, and we do see that. So we have the total sales amount, the amount of commission. We've also calculated the commission percentage based on the total sale price. We have the event, Blue Man Group. We have the buyer and the seller, and then we have the bucket category name of musicals. So all that's been written to Apache Parquet. We'll do one additional create table as. So oftentimes with large data sets, it may be more efficient to query the data in the same way, but partition that data in different ways depending on your queries that you're going to write against those aggregated data sets. So if you typically use pattern of where predicates to query that data, if you have more than one pattern, because S3 storage is so inexpensive, it may be worth partitioning it 2 different ways, which will speed up your query. You'll query less data. In the long run, you'll probably save more money, depending again on the size of your data set, the number of queries that you do, and the where clauses that you use. So let me go back to Athena. We'll run a second create table as. This create table as is going to aggregate the ticket sales by date. So instead of using the category group and category name, aggregating the sales by category, we're going to aggregate the sales by date. So we're going to perform a nearly identical query. We're going to write Apache Parquet snappy compressed. We're going to write it back to the gold area or aggregated area of our data lake. And this time we're going to write it to the ticket sales by date area. We're going to partition that data first by year and then by month. The query is almost identical to the second query, but in this case, we're going to be partitioning the data differently. So same query, different partitions. The idea being that sometimes we will query that data most often by the category group or the category name. Other times we will be querying that data by the month and the date. If those are two common ways in which you query the data, then writing the data back, the same query with two different partition schemes may be more efficient, may save you money in the long run. Again, since S3 storage is so inexpensive, having that data partitioned two different ways can save you time and also save you on the amount of data that's going to be returned when you write your queries. So that query ran, it took about 7.5 seconds. If we go back to S3, we see now that we have two areas of data. So we have ticket sales by category, which was the first create table as query we ran. And then we have ticket sales by date, which was the second create table as query that we ran. If we go into create ticket sales by date, we'll see that parent partition is year and the child partitions are by month. So we have month. In this case, the months are not numeric. They are by 3-letter string for each month. So that's how they've been partitioned. We could have done some ETL and transformed that month into a numeric value. And that would be a very common ETL operation that you might run on the data, preferably to have a numeric value for the month instead of a string. But in this case, they are strings. So when we partition those, we now have 12 partitions representing each month. Within each one of these months, if we were going to example the year 2020, the month of August, I would expect to see that all the sales in this single Parquet file fall within the month of August in the year of 2020. So if we just take a quick look at that to verify that our partitioning worked and the data was properly partitioned. Again, we'll just use JSON. We'll look at the first 5 rows of data or objects in that file. And we can see, in fact, that we do have sales August 2nd of 2020, August 19th of 2020, August 13th of 2020. So it looks like that works. So now we have data in our data lake. We have 2 data sets that are ready for our data scientists and data analysts to use. They are also welcome to use the silver or refined data and write their own queries. By doing a little extra work by writing these 2 queries back to the gold or aggregated section of the data lake, we have done what is a fairly complex query, having prior knowledge of how the data should be joined to the foreign key relationships. We're able to write a join across those 5 or 6 different tables. We're able to write an aggregate query, perform the proper casting on that data, concatenating the usernames, first name and last name, and then writing that data back to the data lake in a manner in which the data analyst and the data scientist should be able to write their queries in a very fast and efficient way. So the data is in Apache Parquet format, the data is compressed, snappy compression, and it's partitioned. So we've done a lot to optimize that raw data that originally landed in our data lake in the raw bronze area and make sure that that is in a format that is most efficient for performing analytics on. So you remember that we wrote 2 data sets, both Apache Parquet, both compressed using snappy compression and partitioned, but partitioned different ways. So one we partitioned by year and month for the sales, the other one we partitioned by category group and category name. So what is the advantage of using Apache Parquet? What is the advantage of compressing that data? And most specifically, what's the advantage of writing partitions? So I've written 3 similar queries here. Let me copy those and paste those into Athena, then we'll talk about the differences. So you can see I have 3 statements here. Select star from the aggregated ticket sales by category. So all 3 of these, we're going to be returning the first 10,000 rows of data from our partitioned aggregated ticket sales by category. The first one is just a select star statement. So just return the first 10,000 rows. There's no where statements and we're returning all of the columns. So let's run that and see what the results look like. And not so much the results, what is the timing and the amount of data scanned? We can see that I took 1.2 seconds. In big data terms, this is still a very small data set. So the runtime is probably less important because we're only talking a matter of seconds for running this query against 10,000 rows. We're really not running it against millions or billions of rows. But what is important is the amount of data scanned. So in this case, again, it's a small data set, but we did scan 990 kilobytes of data. So let's run that query again. And this time, let's say we only want to look at shows, which are operas. For the aggregated ticket sales by category, we partitioned it by category group and then by category name. So the parent partition was the category group, and then the child partition was the category name. So in this case, we're going to look at all shows which are operas. And again, return the first 10,000 rows. So we're being more explicit in our query since we know that's all we want. There's no sense returning data we don't want. When we run this query, obviously you expect it to return faster, which it did. What's more important, instead of over 900 kilobytes of data, it scanned 294 kilobytes of data. Because we know that we only wanted to look at shows which were operas, that predicate in the where clause, the category group and category name were pushed down to S3. And when Athena executed this query, it only scanned those partitions. In this case, it only scanned the category group of shows, and more specifically, it only scanned the category name partition or folder or directory of operas. And we know that we had a single Parquet file in each partition. Because we were specific about the category group and category name and those matched our partitions, we only scanned that single Parquet file, so it was much more efficient. So for our third and final query, we'll be even more explicit. Same query query is number 2. The difference being, instead of returning all the columns, we've decided that these 3 columns are the only ones that are important. So what was the calendar date of the transaction? What was the sale amount? And what was the commission? If we run that query, remember this is Apache Parquet format. Apache Parquet is a columnar format. So we're able to query only those 3 columns and return only those 3 columns of information. And again, we're partitioning it by the same way. So we're drilling down into shows, which are operas partitions. Now we've only scanned 75 kilobytes of data. So we went from over 900 kilobytes of data to between 200 and 300 kilobytes of data, and finally down to 75 kilobytes of data. Now, why is this important? Again, these are relatively small data sets. I think the difference is about a second between the longest query and the shortest query. And if these were millions, tens of millions, or billions of rows, you would see a significant time difference. But what's more important is the amount of data scanned is far less, and you're paying for the amount of data which is being scanned in the query time. So your query time is shorter, you're querying less data, the query is more efficient, you're getting the results back faster, and you're paying less for those queries. It's always optimal to write a query as specific as you can. Try and optimize your partitions for the most common where clauses. So whatever you're typically filtering on or using the where clause, using those predicates, try and partition on those so you can push those predicates down to S3 and only scan the data in S3 that matches those partitions, and be explicit about the columns. If you don't need all the columns, don't return them. Again, Apache Parquet is a columnar format, so you can be very efficient in only returning the columns of data that you're specifically interested in using in your analysis.